Okay, so hello everyone. So welcome for joining us today for the FLOW seminar, where FLOW stands for Federated Learning One World Seminar. And today we have Kumar Kshitij Patel as a speaker. He is a PhD student with Nati Srebro at TTIC in Chicago, and is working on distributed optimization. And today we'll talk about optimal communication complexity in distributed non-convex optimization. So thanks for having you, and can start. Thanks.
Yeah, thanks, Sebastian. Hi, everyone. So I'm Kshitij. I'm going to talk about some recent work in distributed non-convex optimization. So this is joint work with Ling Xiao Wang at TTIC, Blake Woodworth, who was at TTIC, is now at INRIA, Brian Bullens, who was also at TTIC, is now at Purdue, and Nati Srebro. So, okay, even though this is a federal learning seminar, I just give some introduction for people who are watching it on YouTube. So we live in an increasingly connected world today, and I really like this particular number. I like to throw it every time I'm giving this talk. So in 1984, the total internet traffic was about 15 gigabytes per month in the entire globe. And by 2014, it was like per user 15 gigabytes per month. So there's been a massive growth in the amount of like internet traffic. And of course, this is a new world with a lot of data. And like there's this famous infographic which shows that how as humans, every minute of the day, we are interacting with these internet services and generating data with Google, TikTok, Instagram, etc. And more importantly, compute has become really cheap, both on edge devices, which we keep in our pockets, as well as our computers and other devices like. And another like really drastic comparison here is, so the computers which we used to launch Apollo 11 almost like 3-4 decades ago, like they were thousands of times slower than the recent iPhone. So the amalgamation of all these three things means that collaborative learning has become much more lucrative, and it's feasible to do collaborative learning on these edge devices. And we are seeing lots of interesting results because of this coming out. So for instance, one area of research I really like is collaborative learning for basically large scale medical collaboration. So these are medical collaborations between thousands of institutes. These are like studies of unprecedented scale, and like there's a lot of data which otherwise would not have been possible to pull together by a single institution. And collaborative learning protocols, especially ones which preserve privacy, which is where federated learning comes in, are becoming more and more popular in these kind of investigations. And in fact, it's become so popular that now companies like NVIDIA have started offering federated learning as a service to hospitals and other scientific institutions to be able to run these research projects. And yeah, I think there's no doubt that federated learning has become quite popular in the last few years. So what's this talk about? This talk is about optimization guarantees, as was already clear in the title. And we'll be focusing on distributed non-convex optimization. So in particular, we'd be giving optimal guarantees in the full participation setting, which is basically akin to the classical distributed optimization setting with some machines or some data centers, etc. And this is going to look very similar to what some people describe as cross-silo federated learning. But federated learning is not limited to just data centers or talking between several computers. Federated learning primarily became popular because of millions of mobile devices, all of which, as I said, interact with a lot of data on the internet and generate a lot of the data, and are the devices which are closest to people who are generating that data. And training on these millions of devices is both financially and in terms of revenues a very lucrative option for all these companies. The problem is, okay, these devices, even though there's a lot of data, these devices are very sporadically available on the internet, and there might be constraints in terms of what they can share because of the bandwidth they have access to, etc. So we also consider another setting which sort of tries to capture this, which we call the partial participation setting, which is when only a subset of your devices, let's say coming from some meta distribution, are able to participate in the optimization process. And again, this has been referred to as cross-device federated learning. So cross-silo meaning between data centers, cross-device meaning between mobile devices. Our primary focus is in understanding non-asymptotic convergence guarantees. And in particular, the kind of thing which we're trying to capture here is under what kind of assumptions between the client's objectives can we show better guarantees when you collaborate versus when you don't collaborate. Uh, One important point I would like to highlight throughout the point is we are trying to answer the question, are local update algorithms useful? We know they're useful in practice, but are they useful in theory? And this simple question has been surprisingly hard to answer. Even in settings such as convex optimization, we still don't have a very clear picture of when are local update algorithms actually much better than the trivial baselines. And an example is this recent paper in the convex setting, which was trying to basically capture the unreasonable effectiveness of federated averaging. I would say that our paper is sort of trying to make the case for local update algorithms in the non-convex setting for heterogeneous data. Okay, so let me briefly summarize our contributions before jumping into the talk. So firstly, I think we rigorously formalized the current state of results for non-convex distributed optimization. And as I said, there have been several publications in federated learning over, I think in 2020, there were 3,000 publications or something like that. And clearly because of that, there's been a lot of noise in the literature in terms of rates and assumptions and whatnot. And we hope that our work formalizes it and clarifies some of the concerns there. We provide lower bounds, which provide a much needed baseline, because there have been several algorithms and several baselines, but several algorithms and analysis, but there haven't been many lower bounds to compare them against. We also provide an optimal or almost optimal algorithm in the full and partial participation settings, which I mentioned. And by doing so, we sort of established the state-of-art theoretical weights. Okay, so let me now quickly jump into the setting I'd be considering in this paper. So, okay, we have an optimization problem which is defined by M machines objectives. So there are capital M machines, and each of them have an objective capital F subscript M. And we assume these are smooth, twice differentiable, and non-convex functions. Each of the machines functions as well as the average function. And our goal here is to find an epsilon stationary, approximate stationary point, which is defined here using the expectation of the gradient norm square. Note that there are several definitions in literature. So this is expectation of the gradient norm square, and there's an epsilon on the right-hand side as opposed to an epsilon square. And in case you get confused by a factor of epsilon square somewhere, this is probably the reason why you're confused. As I said before, we want to capture how are the devices related to each other. So the devices objectives are FMs, and we want to relate that objective with the average objective. But as opposed to the usual assumptions which people have made, which are first order assumptions, we are going to make a more general, more relaxed sort of assumption here, which is that the Hessians on the machine are close to the average objective, and it's actually pointwise bounded by something like tau. Now, tau is guaranteed to be finite because all our objectives are smooth. So in particular, a worst case guarantee on tau is that it can be as big as 2 times the smoothness constant of each machine. And as I said, this is more relaxed than several bounded first order heterogeneity assumptions, which we've seen in a lot of the convex theory. And this is good because there have been recent works which have showed that first order heterogeneity is hard to ensure in real world federated learning data sets and tasks. So, right. Both these assumptions are similar. One is on the gradient, other one is on the Hessian, and they are pointwise assumptions. They are required to hold on every point X in our parameter domain. There are other assumptions which only need to hold, for instance, around the optimal point or in a neighborhood of the optimal point. But these are the assumptions we'd be working with. Okay, so we also consider access to the following oracles. So we are all familiar with stochastic gradient oracles. They are very common and used to study algorithms like STD. We'd be considering something a bit more general. So we'd be considering something called a 2-point stochastic oracle. So given a function G, and think of this function G as the function on the client device FM, it takes 2 inputs, and rather than giving 1 stochastic gradient, it gives you 2 stochastic gradients at the same noise. So Z represents the noise, and D is sort of the distribution on the machine. So if it's a stochastic optimization problem on the machine, you can think of D as the data distribution on that particular machine. And the properties which these stochastic gradients need to satisfy are very similar to what we have for STD. They need to be an unbiased estimate of the true gradient. They need to have a bounded variance. both of them. And the function G should be smooth on average, where the expectation is basically on the data distribution of the machine. And this assumption is referred to as mean smoothness usually. This assumption is very useful in analyzing variance reduced algorithms and also in giving lower bounds for those kind of algorithms. So that was our Oracle model. But how are we actually doing the communication in our distributed optimization problem? And we'd be working with something called the intermittent communication model, which is quite simple to explain. So there are M machines working in parallel. They basically communicate R many times. So every time you see a dense set of arrows between these nodes, between these circles, that's when a synchronous communication is happening between the machines. And between two communication rounds, the machines have access to K Oracle calls. So K Oracle calls here would mean K 2-point stochastic Oracle calls or K stochastic gradient Oracle calls. And they repeat this for R many times. This means that in parallel runtime terms, they run for KR iterations. Okay, so under this fairly standard model, what are some baselines which we need to consider? So yeah, this is going to be important because these baselines are often not compared against, which makes it really hard to put into perspective several papers in this area. These baselines, as I'd show you, while simple, often tend to be optimal for several problem settings. So let's jump into it. Most natural baselines when you're talking about this intermittent communication setting are these mini batch algorithms. So when I say mini batch, think of this large mini batch SGD kind of algorithm. These sort of training procedures were popularized by this paper, I think almost 10 years old now, accurate large mini batch SGD. And essentially what you do is you basically use the parallelization across the machines to compute the stochastic gradient at the same point again and again in order to come up with a large mini batch. So now your mini batch, instead of being the number of machines, your mini batch size is M times K. So K being the number of times you're allowed to query between two communication rounds and M being the number of machines you're parallelizing over. And okay, so large mini batch SGD, which is probably the most common parallel optimizer, is the thing you should think about. And the interesting thing about mini batch algorithms, so I'm going to call a set of algorithms mini batch algorithms, but you can always think of mini batch SGD at the back of your mind, is that these algorithms query their oracles on each machine at the same point between two communication routes. So they basically query at the same point again and again and again to get a reduced variance estimate of the gradient at that point. And then they make an update by averaging or perhaps adding momentum or something like that. So that's mini batch SGD, but there are also variance reduced versions of mini batch SGD, which are crucial here because as has been shown in theory, you require variance reduction to sort of attain the optimal rates under this mean smoothness assumption, which I talked about earlier. And one of the most popular variance reduced version of mini batch SGD is this mini batch storm algorithm. And it was proposed in 2019, and we already know what sort of upper bound this algorithm gets. We also know that in the serial setting, so when you don't have any parallelization, you have a single machine. And if you have a single machine, making local updates or making communication does not make sense, right? Every step is a step on the machine. So in that serial setting, we know this algorithm is optimal. What we don't know is whether this algorithm is optimal in the intermittent communication setting. So when you have this parallelization and then you have K local Oracle queries and R communication rounds, is it still the optimal algorithm to use? And optimal in what sense? So we actually claim that this is the optimal algorithm to use. And this is a very simple result follows from some serial lower bounds. You can basically show that for every mini batch algorithm. And I'm being a bit less clear about what mini batch algorithm is. But if you go back to the paper, we are very formal about what is a mini batch algorithm, which has access to these 2-point stochastic oracles, actually needs to have this lower bound on its second order, on its stationarity guarantee. And you would notice that this lower bound actually matches the upper bound for mini batch storm, which means that mini batch storm is optimal, at least among algorithms which are like in this class of mini batch algorithms. And interestingly, while this algorithm is really simple, while it's just a variance reduced variant of mini batch SGD, most non-mini batch algorithms, so algorithms which are allowed to make queries at points which are different between two communication rounds, do not even beat mini batch storm. So something like federated averaging, which is really popular, or scaffold, or this recent paper called Fed page, was the parallel variant of this page algorithm, which is optimal in the serial setting. All of these algorithms do not beat mini batch storm. And this is often overlooked in many of these theoretical and empirical studies. So yeah, we would like to make the case that mini batch algorithms are actually great. Like at least the current analysis of these non-mini batch algorithms sort of paint a pessimistic picture for me. The pitfall with mini batch algorithms is I've shown you an upper bound and a lower bound, and none of them depend on tau. What was tau again? Tau was the second order heterogeneity of our problem, which basically related how the client's objectives relate to the average objective. But none of the upper bounds or the lower bounds for mini batch algorithms improve with tau. So even if your problem is really simple, like it would benefit a lot from collaboration, you cannot prove that it would benefit from collaboration because the lower bounds and upper bounds don't have any dependence on tau. And this is, if you think a bit more about it, this is not very surprising because mini batch algorithms are very secular in terms of how they pluck the stochastic gradients from different machines. Like they treat each machine actually very similarly and then just get an unbiased estimate of the averaged objective. They do not really demarcate between the machine's objective very much because they're sampling they're basically getting the stochastic gradient at the same point across all the machines as opposed to getting it on different points on different machines. So this leads to the question, can we show a lower bound that depends on tau for algorithms which are not mini batch algorithms? And more importantly, do we know algorithms that improve with smaller tau? Because this is in the end the goal. We want to develop algorithms which improve when your problem gets easier, which improve when collaboration makes more sense, which improve when the average and the client objective are really close. And fortunately, the answer is yes to both these questions. And the class of algorithms we need to be looking at is something like federated averaging, which is like local update algorithms, the algorithms which allow making several updates between communication rounds, or in other words, they allow querying your oracle at multiple points between communication rounds. So let me give you a bit more clarification about what are local update algorithms. So recall that in the intermittent communication setting, you have k oracle calls between two communication rounds. And a very basic mini batch algorithm is just mini batch SGD, whose pseudocode you see here. And note that mini batch SGD queries the oracle k times between the communication rounds, but it queries it every time at the same point XR. It does not change within the communication round, which is fine. Okay, this is how mini batch SGD works, and this is why it's a mini batch algorithm. But something like local SGD or federated averaging actually queries the gradient at different points within the communication round. In particular, there are these k local steps. And what local SGD is doing is, after synchronizing at the start of the communication round, it's sort of running independent SGD trajectories on each machine. And at the end of the communication round, it's averaging the final iterate on each of these machines and then synchronizing it back and reinitializing and so on and so forth. So the intuition here is that local SGD is somewhat more efficient. It's less wasteful because it uses these oracle queries in a manner which gives it more information about the local objectives, as opposed to mini batch algorithms, which just keep querying it at the same point again and again and just keep reducing the variance of the stochastic gradient estimator. So one important thing is local update algorithms, specifically like the kind I have here, federated averaging, they actually generalize mini batch algorithms because you can always, like if you're allowed to query at different points between two communication rounds, then of course you can choose to query at the same point if that makes more sense. And we again formalize this a bit more in the paper. But what was the goal of understanding local update algorithms? The goal was, okay, can we come up with a class for whom the lower bound for that entire class of algorithms actually depends on tau, which is the second order heterogeneity constant. And we actually show that this is indeed the case for local update algorithms. You would note that for local update algorithms, we have this dependence on delta tau over R. Okay, I don't think I mentioned what delta is. Delta is just some constant which measures the suboptimality of your function at 0. So think of it as a constant. But the good thing is this, the lower bound does depend on tau, as opposed to the previous lower bound. So if you look at both of these lower bounds together, the mini batch and the local update lower bound, then the stochastic terms are the same. The terms which depend on sigma, the bounded variance assumption, are the same. The terms which differ are these optimization terms. And if tau is a small in particular and k is large, in that case, the lower bound for local update algorithms can be much lower than the lower bound term for mini batch algorithms. But of course, I'm only comparing lower bounds right now. It's not clear a priori if my lower bound is tight. Maybe the local update lower bound is just loose and there's no algorithm which matches it. But of course, that's not the case. So this lower bound is this tight, and like what's the optimal algorithm? It is actually tight, and the optimal algorithm is the algorithm we are proposing. So yeah, so we call this algorithm communication efficient local STD because it seemed like a very prototypical local update algorithm, and it was communication efficient in ways I would show you. Don't worry about reading through the pseudocode. I tell you a bit more about algorithm design eventually. But what kind of guarantee can we offer for this algorithm? And the guarantee we can offer is this. So this is the upper bound I can offer for this algorithm. Of course, it's an informal statement. I've not stated what sort of hyperparameters I'm using, their step size, momentum, and all of that. But all of that information is in the paper. This is the upper bound you can get for this algorithm. And you can note two things here. When sigma is 0, then basically the last three terms are 0. And when the last three terms are 0, you only have the first two terms, which are exactly the terms you had in the lower bound for local update algorithms. So when sigma is 0, this algorithm, communication efficient local gradient descent, is actually optimal algorithm. This is the best thing you can use in this class of local update algorithms. And even when sigma is not 0, you would notice that the blue terms are still optimal. They match the lower bound. The gray terms also match the lower bound. The only term which doesn't match the lower bound is this red term, delta L over square root KR. And when sigma is basically non-zero, you have some stochasticity in your oracle calls. The third term dominates the second term, and hence you have some slackness compared to your lower bound. But okay, this is still interesting. Like as far as we know, this is like the first algorithm which is like optimal for even the exact setting, like sigma equals to 0 setting for this non-convex optimization with bounded second order heterogeneity. Okay, let me tell you a bit more about what the algorithm is actually doing, what's at the heart of the algorithm. And there are two major components about the CLSTD algorithm. The first component is this variance reduction term VR, which is based on the STORM variance reduced estimator. So STORM is a variance reduction algorithm which is known to be optimal in the serial setting. And the other component is this local gradient estimator, which you get when you make local updates on the machine, which is based on another variance reduced algorithm called SARA. And the whole name of the game is to combine both of these variance reduction algorithms in a way so that their analysis can get to this optimal rate I showed you. The interesting thing is when you do not make any local updates, then the CLSTD actually reduces to mini batch storm, but with a smaller batch size, with the batch size n. Okay, so where do we exactly benefit from second order heterogeneity assumption? Because somewhere in my approximation of VR and VRKM, I must benefit from a smaller tau, right? In order to get a rate which depends on tau. And it happens in the following way. So basically the estimation error of the local gradient estimator can be decomposed in two terms. The first term actually measures the variance reduction term VR's error, and it goes away. And it goes away. It goes to 0 as R increases, because as R increases, you stop moving. And when you stop moving, this term goes to 0. As for the other term, there's another term which it decomposes to, which depends on tau, as well as the difference between two consecutive local iterates on some machine for some communication round. And again, as R increases, you do not move even locally on the machine, and this term goes to 0. But what's interesting here is if tau is really small, like if tau is much smaller than L, which is the smoothness constant, then you can make this estimation error, you can keep this low by basically using a large K. So that's where we are able to use the fact that if we have a smaller second order heterogeneity, then we can give a better guarantee for the algorithm. as I mentioned, like CLGD is the first optimal algorithm in the exact setting under this assumption. And there have been several algorithms also analyzing this problem. Some of them have also assumed the second order heterogeneity assumption. One paper in particular is this BBR-LSTD paper. So I told you that our crux of our idea is using these two variance reduction algorithms in a very specific manner. And it's not surprising that you can use them, some other variance reduction algorithms in a very specific manner as well and get to similar looking rates. And that's what BBR-LSTD does. They don't analyze the deterministic setting, but we analyze their algorithm for the deterministic setting and also show that they attain the simultaneous optimal deterministic guarantee. In terms of the stochastic guarantee, also they attain something very similar to CLSTD. So in terms of guarantee, we can show CLSTD and BBR-LSTD are similar in the intermittent communication setting. This is not very surprising because if you go to the serial optimization setting, we know several variance reduced algorithms which look very different on the surface, but they attain similar guarantees, which are like optimal guarantees under mean smoothness assumptions. The catch here is that even though these algorithms are equivalent in the intermittent communication setting, the way BBR-LSTD algorithm is designed, it requires several heavy batch operations. So if you're familiar with variance reduced algorithms, these algorithms often have an initialization step where they use a really huge batch size to get an estimate of the gradient, true gradient. Sometimes it can be like the true gradient. They are calculating the true gradient. And later on, they don't calculate the true gradient. They only calculate the gradient at one data point or something like that. Now, some variance reduced algorithms need to do this heavy batch operation several times. The other ones require this just once. Storm requires it just once. And since CLSTD is based on Storm, we require it just once as well. BBR-LSTD requires it several times on the other hand. And experimentally, this becomes this becomes important because all these rates are sort of ignoring numerical constants. And even though they might be similar in the intermittent communication setting, these constants can create a big difference when it comes to actual runtime of the algorithm. So what I can do is, I told you CLSTD only requires one heavy batch operation, as I like to call it, and BBR-LSTD requires several heavy batch operations. But you can always basically split a heavy batch operation across communication rounds and compare the algorithms in the intermittent communication setting. And that's what we do. And what we find is that even though at the end of the day, both these algorithms converge to sort of similar training losses, the pace at which CLSTD algorithm converges is much more quicker in terms of the number of communication rounds required. And this is an important point because this essentially what we're seeing here is a similar convergence guarantee, but experimentally something very different can happen. And you can actually compare them against all these algorithms. Some of them are local update algorithms, some of them are mini batch algorithms. And we notice that as we vary the heterogeneity level of our data on the x-axis, then BBR-LSTD and CLSTD perform roughly similar, which is better than all these other algorithms. Okay. So before I jump to this next setting, are there any questions? Yeah, I think I'm already.
I don't know. I mean, you can, if somebody on Zoom has a question, I can unmute you, or you write it in the chat. So maybe just to clarify, I have a small question. So you were very quick on this slide where you showed the actual algorithm. So to this local, you have these variables V to reduce the variance globally and locally. And can you comment a bit what happens when you go from one round to the next? So after these, do we need to initialize them from scratch after a round of communication, or need to carry over the previous estimate, or what is?
Right. So if you notice line 12 in particular, is the algorithm, are you able to read the lines in the algorithm?
Yes, we can see, yes.
So if you look at line 12, what's happening is, so you are actually carrying over. So after when you start the sequence of local updates on some client M tilt, you're actually carrying over the VR which you calculated right before that. And after these local steps are done, what you do is you take the last local iterate, look at line 19, and then you get some estimate XR plus 1. And this XR plus 1 is where you calculate your mini batch gradients for the next round. So in the lines 6 to 9, there's basically a variance reduced mini batch gradient being calculated. And it's calculated on XR plus 1 as well as XR, since you're doing like two point stochastic queries. So one at the current point and one at the previous point. So yeah, it does get carried over. And like the flow of the algorithm is roughly the following. Like you basically in lines 6 to 9 calculate some VR gradient estimator, which uses a stochastic 2-point oracle. So in line 9, you can see we are calculating the gradient at XR and XR minus 1 at the same batch BRM, which is to say at the same noise BRM. And then you pick a machine randomly and like uniformly at random from the capital M machines and make the local updates on that machine. And then you get XR plus 1 and so on and so forth. And what's basically analogous here to serial variance reduced algorithms is line 9 and line 14. Basically, line 9 is similar to this storm kind of algorithm, and line 14 and 15 to this other variance reduced algorithm. So that's the workflow here, roughly.
Okay, thanks for clarifying. That's good. So there was one more question in the chat, and it was on the slide where you showed these experiments. What was this example task that you showed? I mean, was it a
Right. So it was this task. Both these tasks were Sifartan, and I think I was using a multi-layered perceptron model with 3 layers or something like that. Yeah. And in the second task, the way I'm generating heterogeneous data sets is basically I take the Sifartan dataset, and so this is pretty standard protocol, I think. And there are 10 machines, and because there are 10 labels in the dataset, and now each machine has some fraction of their dataset coming from the global pool of the dataset, and some fraction of it coming from just a single label. So machine 1 gets the first label, second one gets the second label, and so on and so forth. And what I'm varying on the x-axis is as I move from left to right, the amount of data which comes from a single label is growing from 0 to 1. So while I'm moving from left to right, basically the heterogeneity of my data set is increasing, because now on the extreme right, all the machines will only have data for a single label. So even though there would be some similarity between the data sets, like it is different. Like there's a different label, right? Okay, there's one thing I should mention, maybe for people who are interested in experiments. This sort of way of generating heterogeneity where you split the data set based on labels. There have been some papers which have claimed that this is not very honest to how actual heterogeneity occurs in real federated learning tasks. So like when you're, for instance, trying to do next word prediction on a mobile phone of an Android user, it's not the case that they have data from some particular label or something like that. Like there's some mixture happening, and these sort of heterogeneity constructions, the way I've constructed it here, can be a bit pessimistic sometimes in trying to capture real federated learning tasks. And there are like some benchmark data sets which people do run their algorithms on, which claim to be more honest to that kind of heterogeneity. But yeah, this is what I have here.
Okay, no, thanks for the clarification. I think that's very helpful. And yeah, we are now ready to go into the last part.
So yes, so far what have I shown you? So I've shown you that I've shown you that this CLGD algorithm. So we are in the full participation setting. This is like everything I've said so far is about this data. It can be like, you can think of this data center setting where you have several data centers across the globe, and typically they have good internet, and they have like good like they don't have many memory constraints, like they're owned by rich companies, so they can or they can afford to communicate every time. They aren't sporadically available. And what I've shown you here is that our algorithm is either optimal or almost optimal in that setting. But the example of mobile phones doesn't really fit into this category. Like, people use their mobile phones across the globe very differently. Like, there's day in one part of the globe and night in other part of the globe, and thus it's not homogeneous in the way, like, the device availability is not homogeneous across the globe, across different regions. Because of varying internet availability, it's not homogeneous either. So this is why cross-device federated learning has been proposed. And what this setting tries to capture is all these learning problems where you have an extremely large number of devices. Think of all the Android or iPhone users in the world, because I can tell you that these mobiles actually use federated learning algorithms today for several problems which these smartphones are able to solve these days. So cross-device FL deals with extremely large number of devices, and with extremely large number of devices, it makes sense to think for distribution on top of devices, like, because uh, yeah, the capital M assumption, like the finite assumption I had, doesn't really capture it so well mathematically. And this is what we do. So you have a distribution calligraphic P over the machines, and we assume that the number of devices is so large that the probability of sampling from basically the same machine from this distribution twice in simultaneous steps is really low. And this is not very unreasonable if you think on scales of all Android phones or iPhones in the world. But I should say, there are other settings which have tried to capture the partial participation setting as well. This is what we'd be working with. Now, one very interesting thing is that as opposed to the full participation setting, it is now unavoidable to make a first order heterogeneity assumption here. So you notice I'm restating the first and second order heterogeneity assumptions here because the objective has changed. So now these assumptions are like, the first assumption, first order, is only expressed in expectation. The other one needs to hold for all machines in support of P, but we need to make both these assumptions. All the rates I showed you before only needed to make the second order heterogeneity assumption. And when you see it the first time, this comes off as a limitation, because I already told you that there are certain tasks where this first order heterogeneity assumption doesn't really hold. But even though it doesn't really hold, local update algorithms perform well. So is it reasonable or not? For the scope of this talk, I'll not get into this question. What I'd show you is that in the setting I'm considering, this is not just sufficient, but this first order heterogeneity assumption is necessary, in the sense that it appears in our optimization lower bound. And for simplicity, I'm going to assume sigma is 0 throughout this section. So this is not completely unreasonable, because in cross-device FL, you're often working with settings where the scale of the data set on each device is much smaller compared to the total number of devices. Like each user might click like 5 pictures in a day, but there are millions of users doing that. So you are very well able to calculate the full gradient on the data set on the device, but you can't do it across all the devices at once. So we're going to assume sigma is 0, but we have a positive zeta. And similar to the workflow we had in the full participation setting, here we can show the following lower bound for all mini batch algorithms. Note that all the sigma terms are 0, so they've gone away. But there are 2 additional terms, zeta square over mr and zeta delta L over mr to the power 2/3, which actually come from the sampling of machines from the distribution CalP. And this lower bound holds for all algorithms, mini batch algorithms. Fortunately, we are able to show, so this rate, I don't think this was known before, that mini batch storm in the partial participation setting matches this lower bound. So again, it is the case that even for partial participation, mini batch algorithm, mini batch storm in particular, is optimal. But what happens, as we shown before, like, there is no dependence on tau here. There is no benefit to be had from having a problem which is more affine to collaboration. So what really can local update algorithms do in this setting? That's the interesting part. And we can show this particular lower bound for local update algorithms. And you'd note that the first two terms are again the optimization terms. These terms are very similar to what we had before. And the other two terms, in particular, they look similar to the mini batch lower bound, but the last term is actually much lower than the mini batch lower bound's last term. So notice the last term here, it's zeta delta L over MR, while here for local update algorithms, it's zeta delta L over MKR. So provided our lower bound is not loose, this seems to indicate that even in the partial participation setting, you can expect local update algorithms to perform much better compared to mini batch storm. And there are two reasons to believe that. One is that there's this more desirable dependence on tau, and the other is that the dependence with the term with zeta is also much more favorable. And we can actually show an upper bound, which sort of matches the lower bound we have for local update algorithms. And the algorithm we use is a partial participation adaptation of CLGT. You note that the first three terms are optimal here. They match the lower bound. The only term which doesn't match the lower bound is this last red term, which has a dependence on tau as opposed to the dependence on L in the lower bound. And what this is telling you is if tau is small, in particular, if it is smaller than L over K, then CLGD is again optimal. If it's not smaller than L over K, then okay, it's almost optimal. It's optimal up to this last term. Okay, if you ask me whether our lower bound is loose or the upper bound is loose, my conjecture is that our lower bound is actually loose and the upper bound is again optimal for all values of tau. But this is not something we've been able to show so far. Okay, to summarize, so these are the rates in the partial participation setting. The first two rows are mini batch algorithms. So there are no gaps there. The last three rows are basically CLGD and our lower bound, as well as this other famous paper, MIME. MIME was again motivated by a very similar idea. They wanted to capture the benefit which you get in your optimization problem for a small value of tau. But as you can see, our rate is better than MIME. So the first three terms actually match the MIME rate. And that's not surprising because the lower bound also has those terms. So you cannot expect to beat those terms. And the last term is actually better than MIME by a factor of m to the power 1/3. Which can be a lot if your m, the number of machines, is large. So that was the partial participation setting. To summarize, basically, we showed here that our algorithm, again, is either optimal when tau is small, or it's at least almost optimal when tau is not tau is bigger than L over K. And that sort of summarizes things. To again put things in perspective, we basically showed lower bounds, which in my opinion, provide a very important baseline for several algorithms. Like intermittent communication setting has been studied for almost 10 years now, and non-convex guarantees in this space have been studied for at least last 4 or 5 years. I've seen personally at least 20, 25 papers in this domain showing several rates under several assumptions, but these lower bounds sort of give us a way to compare against, compare those rates against what's the best thing possible. Low bounds are also important for theory because low bounds tell you how to do the hyperparameter tuning to sort of match them for the from the upper bound perspective. So that's like one added benefit. We showed that our algorithm either matches these low bounds or is almost optimal in several settings. And in doing so, across both these participation settings I considered, we've established, I think, that state-of-the-art theoretical rates. There's several open questions. One is something I mentioned. When sigma is 0, our analysis doesn't smoothly reduce to the deterministic or exact setting. There is this term delta L over square root KR in the full participation as well as the partial participation setting, even though I didn't show it to you in the partial participation setting, which is loose, and we don't yet know how to get rid of it. Another thing I mentioned is that the partial participation lower bound seems loose. In particular, it has this dependence on L over K, while the upper bound only depends on tau. And we believe that the lower bound can actually be improved. And finally, the assumptions are a bit restrictive in the partial participation setting. Like I did not emphasize this too much, but if you go back, I've already showed you that the first order heterogeneity assumption is necessary, not just sufficient in the setting. Like if your zeta is unbounded, you cannot hope to optimize to arbitrary precision here. And so that part is fine. Like even though it's a bit restrictive and we know many problems don't satisfy this assumption, in this problem formulation, it is necessary. But the assumption which we find restrictive is that the second order heterogeneity assumption, we require it on the entire support of the distribution, as opposed to on average, like the first order heterogeneity assumption. And this is something we would like to take care of going forward. Yeah. Yeah, I think that's it. Thanks for your time. And if you have more questions, please go ahead. Yeah, thanks.
Thank you very much. Very informative talk, and I think also very clear what the results are. So we have a bit of time to take questions. I don't know, either from the chat or people can raise their hand in Zoom. And okay, I see you. Maybe you open now the chat window, so you can see there is one question from Khalil who asked about the term optimality and how you used it. So can you see the question or?
So the question is, you use the word optimal. As we know, a set of achievable objective values is, if feasible, X is optimal. If fx is the minimum value of the achievable set. What is your achievable set? And what did you get the optimal, such as set of client selection or data set? Okay. Okay, so I'm not sure about the first part of the question, but I think I can. Yeah, Khalil, if you can unmute yourself, I think that might be better. But in the meanwhile, let me answer the second part of the question, which is, what did we show to be optimal? So maybe look at the partial participation rate. Where's the table? Yeah, so note that here I'm talking about the full convergence guarantees. So I'm not claiming that just the sample complexity or just the communication complexity of the problem are optimal or close to optimal. For instance, if you look at the first term, delta tau over R, so I'm looking at the last two rows here, then the first term is the only term which basically you cannot reduce by using a very large K. So in particular, if K were very large, okay, so here the third term also, if K were very large, the second and the fourth term in the lower bound will go away. But the first term won't go away. So the first term sort of poses an unavoidable constraint on the communication of your problem. So you need, at least, if you want to get to an epsilon approximate stationary point, then you at least need delta tau over epsilon communication rounds. And one thing which I'm claiming we are optimal in is in terms of the number of communication rounds we require. But in the full participation setting, for instance, we are also optimal in terms of the number of oracle queries we need to make. So if I go back to this rate, then if you only look at the blue terms when sigma is 0, then the first term basically imposes communication complexity. So you get delta tau over epsilon, lower bound on communication complexity. That basically comes from this lower bound which appears before. But you also get a sample complexity lower bound. So to get to an epsilon approximate stationary point, you need something like delta L m over epsilon. So I multiplied and divided by an m to get to the total number of oracle calls. And you notice here that both the oracle and the communication complexity is optimal. So those are the things which are optimal. I think the other question was about.
Yeah, I think that was more like you show here optimality of an algorithm and not of a solution. So I think it was just terminology. So we can.
Yeah. Okay. Yeah.
Skip it or take it offline. So are there more questions in the chat or from people on Zoom, or otherwise? And there are also people in your room, so maybe you can take a local question if there are. Not at the moment. Okay. Yeah, that's good. Okay, maybe so just to be the general picture. So here you used a lot. There's a technique of variance reduction, and for this you need to assume smoothness of the components and the objective function. So can you comment a bit on the results that might be achievable if we don't have smoothness? Or
So if we don't have smoothness of G, or you don't even want the smoothness of capital F?
I don't know, any
So okay,
any
so let's
comments?
say if G is not like this mean smooth. So if we go back to the serial setting, then what the rate you can get in the serial setting is something like you require at least 1 over epsilon square oracle queries in the serial setting if you do not have mean smoothness. But if you have mean smoothness, you require 1 over epsilon to the power 3/2 oracle queries. So there's 1 over square root epsilon gap between having and not having the mean smoothness assumption. Uh, and that sort of translates here as well. Like if you look at the rate you can get for federated averaging, which actually does not benefit from mean smoothness, in the same way as SGD doesn't benefit from mean smoothness, you get a term which looks like sigma square delta L over MKR to the power half, uh, which basically reduces to a sample complexity of 1 over epsilon squared. So if you don't have mean smoothness, then you should be able to get the same communication complexity, but at the cost of a higher sample complexity. If you don't have smoothness altogether, like if capital F is not smooth, yeah, then I'm not completely sure what we can achieve here. Maybe we can work with some expected notion of smoothness, like the function is the gradients are Lipschitz in expectation or something like that, but not much more beyond that.
Okay, no, thank you. That's
Yeah, but one more comment I can make here is this: even though this seems very restrictive, like the first time you look at it, if each machine is actually solving a stochastic optimization problem where uh, the loss basically is sort of smooth, the loss function is smooth, and the randomness is coming from the sampling of the data points. Think of some supervised learning task. Then this is guaranteed for free. Like then you get mean smoothness for free because your loss function is smooth. So uh, G is basically the gradient of the loss function at some specific data point. So yeah. But yeah, I think this is an open question. Like I think it's not known how to guarantee even in the serial setting using just SGD, how to get the optimal rate which you get using mean square smoothness assumption. Like that is not known as far as I'm concerned. And yeah, I think that sort of translates here as well.
Yeah, okay, thank you very much for this good answer. Yeah, that's interesting to, to see where are the limits of all this.